In this video, we're going to take a look at configuring and breaking down the background information to virtual links. Now, if you've never heard of a virtual link, or you think it might be making up things, a virtual link is 100% a real. It's real. It exists. Basically, what a virtual link does is it takes the inherent break that can happen when you have multiple areas connected to each other, and you happen to have an area that is discontiguous from area 0, meaning that the area you've got configured does not have a router that's got an interface inside of area 0. Now, if you have a situation like this is what they refer to as a discontiguous area, because in order for an area to be able to reach the backbone, the ABR that connects your area to area 0 must be at least one interface in area 0 in order for it to work. So if you don't have that, you have to set something up in order for you to be able to reach the discontiguous area, and a virtual link is how you do that. Now, a virtual link is really easy to configure. It's one line of syntax underneath the OSPF process, and when you're dealing with OSPF version 2, which is what we're dealing with right now, it's available for IPv4. When you're dealing with OSPF v3, it's only available in IPv6. So we'll take a look at that when we get into the IPv6 stuff, which I'm going to group that together in a specific IPv6 section. But it's actually really easy to work with. I mean, it's one line of command, and it's a one line of syntax to get it operational, and then that's all there really is to it. So basically the idea is, when you're dealing with virtual links, SPF is not run to reach the ABR's advertised inter-area routes. So basically you use the intra-area shortest path tree to the ABR and add the ABR cost to my shortest path tree cost. So what if the ABR isn't reachable via the shortest path tree? And this is the problem we run into. So if you can't do these first 3 lines right here that I just read out, then you have a problem. So the idea now, in certain states, cause ABRs to be unreachable. So if you do have a situation where an ABR is not reachable, and remember, we use the ABR in order for a router to be an ABR, it must have at least one link in area 0. Now, what you're actually going to be doing is you're going to be creating a router that is technically bordering two different areas, but doesn't have a link in area 0. What you're actually going to be doing is you're going to be going from an ABR that does have a connection in area 0, and you're going to be using what they refer to as a virtual link. And that virtual link is actually going to be just a unicast adjacency that goes over the non-backbone area to the router that connects the non-backbone area to the discontiguous area. So the idea is that when you have, say, router 1 is in area 0 and in area 1, and you have router 2, which is in area 1 and area 2. So you need to be able to get a peering between router 1 and router 2. As long as router 1 can recurse to the router ID of router 2 via type 1 LSA, then and vice versa, router 2's got to be able to talk to router 1. If that can happen, then you can form a virtual link. So what that also means is that your routers you're trying to form the virtual link over don't have to be directly connected. As long as, and what I mean by that is, if router 1 and router 2 are physically directly connected, so there's a wire going directly between them, or there's a switch in between them, or something that allows the router 1 to learn router 2's router ID and vice versa, you can have a second, third, fourth, or even 6 routers in between, as long as the ABR touching area 0 can see the router that's touching area 1 and area 2. As long as that router can see that router's type 1 LSA for its router ID, that's all that matters. And I say that only because of the fact that you're going to be advertising that as the advertising router's information. I say that type 1 LSA just so that it's a LSA that's advertised for a connected link, when technically speaking the router ID is not actually a subnet you can route to. It's because the router ID is just a 32-bit integer, it's a 32-bit number that takes the form of an IP address, but you don't actually have to have a route to. You can give it some really goofy IP address or IPv4 formatted IP address, and it'll still function as a router ID. You just won't be able to route to it. But as long as the ABR in Area 0 can see its router ID, that's all that matters. So, like I said, it either could be directly connected or several hops away. That doesn't make a difference. So, to repair a discontiguous area, you would need a virtual link. So, the most common way you're going to do this is through a virtual connection, which is the VL. Now, there are potential possibilities where you could use a GRE tunnel, where you would configure a GRE tunnel, and you would put both ends of the tunnel in Area 0, and you'd be able to bridge Area 0 over that. I've never really done that before, and I'll test it for a minute to see if it'll actually work, but I think the last time I tried it out, it blew up on me and it wouldn't work. So I'm not sure if that's a limitation of GNS3 or what have you, but it is what it is. So now the virtual link itself, there again it says to use to form multi-hop unicast area adjacency. Again, meaning it doesn't have to be directly connected to each other. So the ABR and the router there will become an ABR. So it follows the already built shortest path tree between the ABRs to heal the database. So the cost is the cost through the shortest path tree to the ABR to the target destination. So whatever the ABR cost is to get to the next hop from Area 0, whatever cost that link gets from its configuration, whether it's the auto cost reference bandwidth or its inherent cost due to bandwidth, that cost is automatically applied to the virtual link. So now the other thing too that's relatively unknown, or I shouldn't say unknown, but known less than what it should be, I should say, is that the virtual link is actually has some optimizations to it. And these optimizations are referred to the demand circuit and the flooding reduction capabilities. So basically what that is the DNA, or do not age, LSA bit is turned on. And what this basically does is it doesn't send hellos. So if you turn on the DNA, or you type in the do not age LSA, or you type in demand circuit turns off the periodic every 10-second hello going across the wire, or going across the connection, I should say. So it automatically disables that. And then flooding reduction, what that does is that actually disables the paranoid every 1800 second or 30-minute reflood of the link state database. So every 30 minutes, regardless of what's going on in the network, OSPF will automatically reflood the entire link state database to make sure that it doesn't get too stale. So what will end up happening is if a link state advertisement gets too old, it could possibly become corrupt or bad information. And remember, the OSPF database has to be synced with every router in that area. And if it's not synced, or there's something that's incorrect in it, then you can run into problems with that. So the idea is actually pretty straightforward for the most part. If you have a problem with the link state database, you can just do a clear process that's going to reflood, and that will usually take care of the problem. So a virtual link automatically by default runs a demand circuit as well as flooding reduction, and we'll talk about those more as optimizations as we go along. And the reason the whole purpose of the demand circuit and the flooding reduction were to for connections like, for instance, back in the day, we're talking like early 90s, late 80s, and mid 90s, back when I was just a kid. It shows you my age. I'm not very old. Back in those days, when you used to have dial-on-demand services like ISDN, to where you got charged for the amount of time that the connection was up. So, for instance, you would dial into your. So, if you were to be at a hotel and you were to connect into like use a dial-up connection to VPN into your company's network. So you would dial into them, and they would hang up and dial you back, so that the company was getting charged instead of you getting charged. That demand circuit, so that dial-on-demand capability, you wouldn't be sending periodic hellos because you would get charged for the amount of data that went across that wire. So for even the very small amount of data that OSPF would send across with hellos and stuff like that, that was data you would get charged for. The same thing with the flood reduction. If you went in there and, let's say, for instance, for whatever reason, you were peering with OSPF over that link, if you kept that link up, you would get charged for it. But if you weren't sending data across it, but the link was still up, there are some services where you would get charged for the link just being up, or just the amount of data that went across the wire. The circuit could be up, but as long as no data was going across it, you wouldn't get charged. The minute data went across, the ticker was going. So the whole idea with the demand circuit was to not send hellos, and the flood reduction was not to send the every 30-minute update. So that takes care of that problem. And you'll see in the link state database that anything learned over the virtual link will have the DNA bit set, and it'll actually show up in the link state database, so you know what that's going on about. So with path selection, the OSPF state machine prefers an intra-area route over an inter-area route. And it also will provide, for external routes, it'll choose an intra-area external over an inter-area external. So that means that if your route, if you have a route to an intra-area route, so an O route, it'll choose that route over an inter-area or an OIA route. So it'll choose LSA type 1 over LSA type 3. Same thing with external routes. It'll choose an intra-area external over an inter-area external. It'll choose a type 5 LSA over you going to, or a type 3 LSA or a type 4 LSA. Because remember, regardless of how you look at it, if you're in that area, you don't have to recurse to the ASBR. So you're going to recurse right to type 5. Because of the fact that you're going to see it as a type 5. But if you have to leave your area to get somewhere else, you're going to go type 3 to type 5, or type 3 to type 4 to type 5, depending on the situation, how you're trying to get there. But that's the idea behind it. So you're going to choose intra-area external over an inter-area external. So the idea is if you have the ability to forward traffic over the right connections, that's the whole point. Now this last one here we have is transit capability. Normally what you're going to do is normal operation as traffic go through the area 0 connection. The virtual link is an adjacency that might be farther away to the ABR using the shortest path tree. Transit capability gives you the ability to use shorter paths to the ABR if available rather than following the area 0 path. Now by default, transit capability is turned on. So this means that you would try to find the shorter path to the ABR. And sometimes a virtual link may not be that case. So, for instance, I won't be able to demo this, but the idea is if you have a connection and you want to choose to route over the virtual link, you can do so, or you can choose not to route over the virtual link. And if the virtual link is farther away, if you could choose no transit capability, and that's going to choose the shorter path over the ABR to the ABR. Now, a couple of caveats that come with the virtual links. There's not a ton of them, but there are a few. So, when it comes to this, endpoints must be reachable via a normal area. In other words, you can't use a stub area. And so that means you can't have a ABR connected to a non-backbone router, and you can't have a stub area configured on either router. So if you have a stub area and you do configure the virtual link, you'll get a unreachable cost. So it'll be 65535 as the area, and I'll show you what that looks like. I'll actually configure it and I'll show you what it looks like. But it won't be in this video. I'll show you some of the. I'll break OSPF down the road, and we'll have to figure out what's going on. And the transit area must not have any filtering applied. You can't be doing any Type 3 LSA filters, and you can't be doing any distribute lists. So, because you could be potentially filtering out what you need to use to get to where you need to be. So if you have a Type 3 LSA filter, meaning you're trying to prevent Type 3 LSAs from being propagated, that could be bad. So the inherits the cost from the shortest path tree between endpoints, and the cost must be below 65535. If it isn't, then the demand circuit or the virtual link will go down. Now it runs as a demand circuit, and errors in config could be hidden until flooding occurs. And I've always had a hard time demoing this, so I'm not even going to bother here. But if you have a problem where if you're not flooding correctly and the information hasn't gone across the wire, then you could have issues with reachability and things like that. Virtual links must be configured on ABRs, and ABR is a router with that borders two areas. ABRs are routers that have at least one link in area 0 and one link in a non-backbone area, and the router IDs are used to form the adjacency. So this is the config. You go to the router that's in that's got a connection to area 0, and you type in area 1 virtual link. You're telling it you're going to be going into area 1, and you want to make it you want to create a virtual link over that. And then you go to the other end of that link, and you type in area 1 virtual link, and you type in the remote address, the remote router's router ID. And that's all there is to it. The virtual link, as long as R1 and R6 can recurse to each other's router IDs, that is all that matters. Everything else comes up. Now I have a bunch of details in here on how this will actually work, and I'll be uploading all these text files for you to be able to follow along with. And then we have some sidebar notes here with the flooding reduction, or the demand circuit, and how it actually works and what it's used for. And we have the flooding reduction, which is basically it doesn't send the paranoid update, and the demand circuit doesn't send hellos. So what we're going to do is we have to do this on the connection between I think I can go back or not. Give me a second. I'll clean up this diagram. So where we're going to do this is right now router 2. Oh, actually that's not what I want to do. 1 second, please. There we go. So router 2 right now is an ABR, or I'm sorry, no, he's not. Router 2 is a backbone router, and router 3 is an ABR, and router 5 is an ABR. So what we need to do is we need to talk between router 3 and router 2, and router 5 and router 4. As long as these guys can peer with each other, and we'll take a look at this and make sure we can actually talk to each other. As long as router 3 can see router 2's router ID, and router 2 can see router 3's router ID, same thing goes down here. 5 should be able to see router 4's router ID, and 4 should be able to see router 5's router ID. If that can happen, virtual links will be able to form, and router 1 will be able to learn all of area 0's routes. So you'll see how that will come into play here momentarily. So the idea is relatively straightforward for the most part. Let me bring up our PuTTY session. There we go. And we'll bring this down. So what we're going to do is we're going to bring this over, and on router 3 we have to type in, let's go to router OSPF 3, and there's a comment, what's up, or the question, what's up with all the messages. I was actually using this GNS3 lab in a different computer, and this is actually a virtual machine that I'm connected to. It was originally on my computer that I'm recording on, and I moved it over to a different computer, and because of the fact that it was just chewing up way too much memory. And I've got a lot open right now because I've got a lot of other projects that I'm working on, and but that's why. So what I'm going to do is I'm going to do a do show IP route. Now I should see router 2's loopback, and right now I don't see that. I don't see router 2's loopback. So let me go to router. Let me do a do show IP OSPF neighbors. And right now, I see his router ID, right? But I don't see his, so I don't see it in here. So what I'm going to do is on router 2, I'm going to advertise that into OSPF. So router OSPF 2. I'm going to type in network of 10.255.0.0, 0.0.255.255 area 2345. I'm going to do the same thing on router 5, router 5 should see do show IP OSPF neighbors, and I should see 4 do show IP route, and I don't see his either, so I need to make sure I have those advertised. And I technically don't have to do that, but I do it because of the fact that I know that I can reach it. So I want to be able to recurse to it. He sees it, but I want to make sure that I can route to it. And I'm going to type in router OSPF 4, type in network of 10.255.0.0, 0.0.255.255 area 2345. So now if I go to 3 and type in do show IP route, I should see router 2's loopback in there as a intra-area route, and I do. And on router 5, I should see router 4's loopback as a intra-area route. That's good. Now what I'm going to do from router 5, I'm going to type in router OSPF 5, and I'm going to type in virtual link, or I'm sorry, area 2345, or and then question mark, and then virtual link, and then the other guy's router ID. So in this case, router 4's router ID. So 10.255.4.4. I'm going to hit enter. Now what I'm going to do is I'm going to go over to router 4. I'm going to type in area 2345 virtual link and 10.255.5.5. Now once that goes across, we should see a virtual link pop up. And we do. That's great. That's a good sign. Now, we don't actually have a pairing between 2, 4, and 1 going yet. I'm only going to do this on one side. And the reason why I'm going to do it on one side is because I'm going to show you how it's a necessary evil. And then once we get all these connections up and running, then we'll do the pairing between 3 and 2, and then you'll see where 1 will have 2 ABRs to go through. So what we're going to do is on router 4, we're going to type in network of 172.16. Actually, let me double check my IP addressing here. Do show IP interface brief and 123. So network of 172.16.123.0 0.0.0.255 area 123. I'm going to hit enter. I'm going to do the same thing on router 2, and I'm going to do a network of 172.16.123.0 0.0.0.255 area 123. I'm going to go to router 1. I'm going to go up here and I'm going to go config T router OSPF 1 network of 172.16.123.0 0.0.0.255 area 123. Okay, so after the wait timer goes off, we should form a pairing, and actually, didn't want to do that. Router 4 should form a pairing as well, and momentarily we'll have, let's make sure all these connections are up and running. Do show IP interface brief. Okay, it is up. Go to router 1. Okay, there I go to 4, and do show IP interface brief. Do ping ping 172.16.123.2 and 4. I just want to make sure I can connect to them. Okay, so I can connect to both of them. That's a good sign. So now if I do a do show IP OSPF interface brief, I am one second. Do show run pipe section OSPF. Oh, that would be why. Okay, that's something I forgot, and I'm actually glad this happened when it did. I can't use, because I basically put this under VRF Lite. I can't do that, so I'm actually gonna have to type in no and pull this guy out. I have to use a different process number on here. So I'm gonna have to exit out of here. Type in router OSPF we'll say 123. Type in network, or let's type in this network command in here. And remember, the process ID is local to the box, so I can use arbitrarily any number I want. And there we go. So that's better. So the problem that we're going to get is that I have VRF light configured between router 1 and 2 with process ID 1. So now if I do a do show run pipe section OSPF, I should have two processes, 123 and 1, and peerings to both. So now I have 123, and then I have network, this guy right here, everything's going. Now what I'm going to do is I'm going to type in do show IP OSPF database. Alright, so this is my link state database. And notice my only exit point here is router 4. I have my intra-area routes. This is my type 1 LSAs. I have my connections to router 1, 2, and 4. So this is what I'm advertising. This is what 2 is advertising and what 4 is advertising. Then I have my network link state. So router 4 is the ABR. Or I'm sorry, is the DR. Router 4 is the DR because he's got the highest loopback address. So his link ID is this guy. So again, with the whole point of the DR is if you can recurse to the DR, you can recurse to anybody in the entire environment. Now, I have my type 3 LSAs, and for area 123, and I have, and don't mind that, router 4 is my only ABR. So I'm learning all these other routes. Now, if I type in do show IP route, I should have a bunch of inter-area routes going to router 4. So if I was to dump down here and do a show IP OSPF database for the summary, and hit enter, I'm going to have the routing bit set for all these guys, and notice who the advertising router is. Router 4 for every one of them. Now if I wanted to do let's do a show IP route again, show IP route, you're going to see that I can trace route to 10.255.16.16. I go 4 to 5 to 16. That all works. Now, let me show you how to finish this up. I'm going to go to router 3. We're going to type in area 2345 Virtual Link 10.255.2.2. Now we're going to go over to router 2. I'm going to type in area 2345 Virtual Link 10.255.3.3. Hit enter. Now I'm going to form a virtual link over that area as soon as it wants to form. Do show IP route. Okay, it should see it. Okay, so why is it down? Do show IP OSPF database. Okay, so I can see that we're learning routes in that way. So as you can see, the link state database is starting to grow. It's gotten significantly bigger since the last time we checked it out. So area 0 that's why I can't see his from router 3 I can't see his type 1 LSA. That would be the problem. So from router 5 if I go to router 5 and I type in do show IP OSPF database, I see router 4's type 1 LSA. I don't see on 3 I don't see router 2's type 1 LSA in area 0. That's the problem. So let's go to 2 and type in do show IP IP OSPF database, do I see router 3's? No, I do not. So let's do a do show run pipe section OSPF. Oh, you know why? I know why. I know what the problem is. Because router 3's loopback is something else. And router 2 do show IP interface brief. That's why. Because the router IDs are incorrect. That's what the problem is. I have a loopback of 200.0.0.2. So I type in do show IP OSPF. My router ID is right here. Yeah, it's right on this side, but wrong on the other one. That's what the problem is. So on this guy, I see this be a 4. The problem is I need to go to 2, and I need to type in, pull this guy out. No, and do show IP OSPF database, and I should see router 3's LSA via this guy right here. That's his LSA. That's the and right here in 2345. Actually, and that's the problem. I'm looking in the wrong area for 2345. I do see the I was looking in the wrong area. That was my first problem. So right here, I see his loopback, but I had the wrong router ID. So I'll type in area 2345 virtual link, and then router 3's loopback. That should form now. Might have to bounce it. There we go. Oh wait. Oh no. Not quite. There it goes. And the reason for that is because it had the wrong router ID. It's got to be all recursive to type 1 LSA in that area. And if you look right here in 2345, actually it's 2345. I see router 3's loopback as a type 1 LSA. If I go to 3 in area 2345 as a router LSA right here, I see router 2's loopback. So now we have that configured. We go to router 1, do show IP OSPF database, the summary, or let's take that one step back. Now we see 2 and 4 as our connections. And we see that. And we see area 0, and we see area, and we see area 123. That's what we're trying to, we see our area, and we see area 0. And we're learning those routes. So we do, let's go all the way to the bottom. We see these links because of the fact that 1 and 2, this is my loopback, this is his loopback, and everything looks good. So now we do a show IP route. We're going to have multiple links. So we could, to get to 24, we could trace route. To get to 35, we could trace route. Let's do a trace route to 172.16.35.5. We're going to load balance across, and we get to where we want to go. So that means we have everything configured as we need to. Now we type in. If you notice here, you don't notice it on this side because it's only traffic going over the virtual link. So we go to router 3 and we jump out of here. We do a show IP OSPF database. We see DNA bits. The DNA are letting us know for area 0 that do not age LSAs are going across, so that we don't send hellos across the wire to these guys, because of the fact that we're sending traffic over a virtual link. And that's the only reason why. You see it's going for 2 and 4 on 3 because he's receiving the DNA bit because of the fact that he's got the virtual link configured. And any routes we learn across that for 2 and 4 are going to be set up to that. So that's how everything would work. Now what we can do is, as you can see, let me bring this up just a little bit so you guys can see it. It'll be a little easier to read, I think. So we have, you can break this down per area too. You can do a database for I think you do topology. No, not quite. Database. You can do internal, but the way this breaks down is from the top here, it goes numerically from the bottom up, or from the top down, I should say. For area 0, then area 2, 3, 4, 5, and then if we had another area, it would be whatever area number comes in numerically, that's how they fall into place. So we have our type 1 LSAs, which is our router LSAs. These are the router LSAs we were learning for area 0. We have our DR connection, which is router 3, which is who we are. And then for our summary network link state, this is our type 3 LSAs. This is the ABR that we're pairing with. So 2, 4, 5, and 3 are all ABRs, and these are the links that we're learning from them. We get to 2, 3, 4, 5. This is the type 1 LSAs here for area 2, 3, 4, 5. The DR, and then the type 3 LSAs. So we don't have anything going on beyond that. So again, if you wanted to, let's say for instance, we wanted to go to router 1 and do a show IP interface brief, and we wanted to create a couple more loopbacks. So we're going to type in interface loopback 101, type in IP address of, let's say 10.255. Actually, what am I advertising? Do show run pipe section OSPF. I don't know what actually we're advertising. I think we're just doing 172.16. Yeah. So what we can do is we can go to, since we're underneath the interface, we can actually type in IP address of 10.1.1.10 and /24. We type in IP OSPF 123 area 0, or area 123. And now when I do that, I go over to router 3 now, and I hit the up arrow. We'll see, as this gets flooded, that we'll see 10.1.1.10, and we're going to be able to trace route to 10.1.1.10. We'll be able to get there because it knows how to get there via router 2, because router 2 is advertising it to us. So we're doing a type 3 LSA lookup. So we're saying in order to get to, we'll do show IP OSPF database for the summary of this link right here. It's telling us that we can go a couple different ways. We can go via router 2, the routing bit is set, and the metric is 2. We have another link via 4, the do not age bit is set, and the routing bit is not set though. The routing bit is only set for router 2, as you can see right here, which is telling us that our best path is via router 2. Now if we were to manipulate the metric to where the cost was higher on that link, or whatever the case may be, we could route another direction via cost. That's the most applicable way of handling it. Or we could do a longer match, because it's actually matching as /32 because it's being advertised as a loopback. So now if we were to go to router 1, and go click on router 1, type in IP OSPF network is point to point. We go to router 3, we hit this guy, and notice the LSA age. I mean, it's very, very short. But now we're advertising it as delete flag. Okay, so it's hasn't been max age right now. It's being flooded. So actually right now we lost it, and we'll have to wait until we get that back. So we have to wait until that happens, and then as soon as we get it back, we should be good. Oh, there. Okay, now it's coming in /24. I was going based off of 10.0. There we go. Because I was going based off the IP address, not the summary. Because now it's being advertised as a /24, not as a /32. So it's being advertised as /24 now, and I have to advertise the entire range for that subnet, not just a particular IP address. And still we're going to be a /24. But if I was to do something like a summary and advertise like a /27 or something like that, or on router 2, if I was to advertise a shorter match, so like a /20, then it would be a router 4 because that would be the longer match. So it just depends on how you want to go about it. We'll get into that more in detail later on, but that's basically how this stuff will work. So it's actually relatively straightforward once you start digging into it. But again, the routing bit is the piece that needs to be noticed. Let me do this and do this. Now that'll be easier to read. So we have the routing bit set here towards router 2 for the summary for the type 3 LSA towards router 2 to get to this particular subnet. So if I want to go, now that I know where to go, I can go to router 2. That's where it's telling me to go. Now I go to router 2 and do a show IP OSPF database for the router LSA of where is it? Router LSA. Let's see. Where are you hiding? Actually, let's do this. There it is. That's what I'm looking for. And I'm going to do for the router of this guy. Oh, nope, not that one. .10. No, it's for. Actually, I want to do. I need to recurse to area 123. I got to go down to the bottom here. For area 123, right here. So for the router, and then that, there we go. So basically for the router LSA of area 0, because that's what we're in right now. Well, actually, no, that's not technically not true. We're actually in area 123, and 123 says for this area 10.255.1.1 in this area. So let me just grab this guy right here and do this. Hit this up area, pull this guy back, and punch this in. So we know how to get to where we need to go. So we have the 10.110 in area 123. We know how to get there, so we can recurse to that. So if we needed to figure out where to go from there, we click on router 1, and we know that we're on the right router. So this is the guy advertising it. So that's how you recurse hop by hop to figure out what's going on. So technically speaking, when I'm on the phone with a client or I'm troubleshooting something, and the client gives me a network diagram of what's going on in their environment, and they're telling me traffic is routing a certain way and they don't know why, or something's going on and they're having a problem with it, all I have to do is look at their link state database and figure out, based off of the routing bit being set and taking a look at their forwarding tables, I can tell them exactly what the problem is. Now, we haven't gotten into any of the advanced configurations yet, and we'll talk about authentication, we'll talk about summarization, we'll get into the stub areas. So we have actually a lot left to cover, and actually if I pull up the PDF here, we actually have a lot to cover. So far, all I've done is I have talked about the packet types. I've talked about neighbor relationships, and I haven't touched authentication yet. I have talked about the different network types right here. It doesn't want to copy. So I've talked about the network types. I've talked about the LSA types. I have talked about the area types. And I've talked about backbone, normal, transit, but I haven't talked about stub, not so stubby, area, and totally stub. I've talked about the different router types, internal, backbone, ABR, ASBR, and I've covered virtual links. I still have to cover stub, NSSA, and totally stub. We'll talk about path preference, and we'll get into IPv6 and some of the OSPF operations. But we still have quite a bit left to cover, and I feel like I'm just getting started here. Because if you look at it, for our entire environment, it's not that big. I mean, we've only got, 8 routers? 6 routers? No, 5, 7. That's a relatively small deployment. But as you can see, we've made it pretty complicated with having multiple areas. With Virtual Link, we're getting the DoNet age bits in there, but we're learning how to recurse. All that type of stuff is coming into play. So at the end of the day, when we start getting into more of the complicated designs, it'll be easier and easier for you to figure out what's going on. So if you were to call me and I was to say, okay, let me remote in and take a peek, I would look at your OSPF database to see what's going on. You're telling me you can't get to a particular route. Okay, do I even see it? If I don't see it in the link state database, it doesn't exist. So that's going to be necessary, and I mean that in regards where, depending on if you're not doing any filtering, like a Type 3 LSA filter, that'll pull it out of the routing database, or the database and the routing table. Where if you just do a summary where you peel it back with a distribute list or a prefix list, that only removes it from the routing table. It doesn't remove the LSA from the database. So we'll take a look at some other capabilities that are out there, but at the end of the day, that's how you have to break down what's going on and get into the details of how the link state database works. That's why I keep harping on the database, because it's pretty much the backbone of how OSPF works. So if you were to give me breakdowns of how things are working, I can say, well, based off of what I'm seeing here, I can go in there and say, okay, well, I know how this is connected, I know how that's connected, I know which way this guy's routing, and I don't even have to, I can like literally draw it out without even looking at a topology or a network diagram. Here it's easy because we have it laid out already. But if you can break down how everything is recursing, then that makes your job so much easier. And this is a relatively small environment. Now imagine if you had 300 or 400 routers all running OSPF and you had one flat area 0. That's why the areas are there, for it to scale. And we'll talk about that more in detail later. So that's the virtual link. I wanted you guys to see exactly how that would work out and then go from there. So I hope this has been informative for you. I'd like to thank you for viewing.